Okay, we can start now. Sorry. Okay. Today we will discuss some visualization of an article. An article talking about the predator ray model with general Hornbeam type tree functional response and combined with a strong alley effect. The other is one is Zen Beiju, published this year. Like now we can. So yeah. So the content of the main papers is performed 6%. The first thing is talking about the positive and boundedness of the model. The second one is equilibrium. That's we want to find the fish voice of the solution of the model and discuss about the stability. The third one maybe they discussed about the Lyapunov function, but different kinds of the paper they could discuss about the global stability. Maybe they don't need to choose Lyapunov function. The fourth thing is this is the main thing of the paper is bifurcation. Bifurcation that well, that's mean they want to discuss the changing around the fish void, the changing of the constant around the fish void. And the fifth one is a reduction number. They choose the coefficient. And the sixth one is our main point. It's a sensitive analysis. At this point, we will perform the solution, perform the visualizations of the solution using Python code. Okay, it's also new to me, and I will summarize some mathematical relation to this paper. In this paper, they discuss about the model predator prey system with a general Hornbeam type tree. As this is the kind of functional response and strong alley effect. Of course, we have weak alley effect model. What does this mean? We will discuss later. First, we need to understand the model. Here is the rate of predator, the rate of predator. And this term, a logistic growth. Logistic growth is normal. And this term is the LED effect. LED effect is also famous and this time. And the last one is Hornbeam. It's called Hornbeam type tree. Hornbeam type tree, okay. It's a kind of functional response. And here is the rate of the rate. And we multiply this and we can see this, the increase rate, the increasing rate of the rate. And minus YD, that means the population will decrease some by maybe by units by birth, something like that. Before using the before discussing the positive, we will rescale the terms by by setting the other coefficient to reduce to give the simplest form of the model. So for detail, could you please investigate and read the paper again? We got another model. The new model is the rate of x. Here is also the term of the role of the logistic role, and this term is also Allen effect. And some constant also has been simplified. Yeah. And the rate of y also expressed in this term, and multiply this. The constant c and d also rescale by some strength form. A simple strength form maybe translation or something like that. Dilation. Okay, in this. We need to know some functional response. Here is the list of 3 types of handling time. The first one is functional response. This is a linear form of the changes. That means the radiator is read in terms of rate by the constant, by contact by the constant. It is a simplest form of the model. And the second one is handling time 2. Handling time 2 is expressed by the function hyperbolic function. This increase associated with the constant, and the constant we can rescale by the constant b, bc, or that the component, the multiplication of the alpha, and alpha is attack rate of the radiator and brake. We can simplify this constant by another constant. And the third one is handling time 3. This is the general form of handling type 2, and this content also rescale by, actually it's m is a component, the component of many constant, and we will discuss later. For the handling time t, we need to have some condition for the model consisting between the interaction of radiator and ray. Okay, and the next one we will discuss about the positive and boundedness. We need to ensure that the models is positive for the values. So and we investigate the boundedness of the model to ensure that we can find the Fitzroy and the solution of the model. Here is the definition about the body for the general problems. S delta is the operator, addressed by function S and T, certifies the initial condition with T in terms of 0 infinity, and 0 also in real number, and ST is a vector in Rn. For the domain D, the set D in the subset of Rn, and F is a continuous nonlinear function. And we say that's the solution X of equation IVB. Equation IVB is IVB. Satisfy the condition T larger than 0. Uniformly embodied provided by constant C. If it's sitting a value C0, certify this depend on C0. That means satisfy the inequalities here. Inequality, the smaller by the constant C. It's look like the maximum value. We need to find the value of S, not on T0 to satisfy in the interval. And the second definition is talking about the equilibrium. How to find the equilibrium points of Fitzroy of the dynamical system. So we have defined the S star. S star is an equilibrium point of a dynamic system at some time t star, and the state vector S star St becomes equal to S star, and then needs to satisfy this condition. So we use this definition by to find the equilibrium points. We need to solve this equation, and this also the solution of function f. Now we will apply to the model. The models, I mean the second model, that's the models we have free scale. So the second one, from the second one, we need to find the equilibrium points and the solution. So we just put them equal 0. How to solve this? Maybe we can use any kinds of application to solve it. In this case, I suggest you to use MATLAB. Matplotlib is convenient. Matplotlib or MATLAB, I think. They list some solution in this case. The solution with the condition. Actually, how many solutions? We need to choose some solution with specific properties. Now with the condition, we need to find the condition of the constant. The condition is based on the Hartley tree with the existing condition. This must be existing for this satisfy the condition with existing delta greater than 0. Use this here the condition of delta. We multiply by the quadratic equation, the quadratic form, and we can find the solution of y and substitute again. So we got what x. Then we have total is how many solutions? 3 solutions. The first one is 0, 0.0 for the first equation, and the second solution is maybe we have x by the constant, and the next one is more complicated here with x and y. Where is X? Oh, I didn't show here. We need to show here. We need to solve this. We need to solve this equation and we can find X star, and substitute again in another equation and we can find Y star. So we can classify by three solutions. That means that called equilibrium. Just put them equal 0. Lucky, we can summarize the solution like this. The first solution is 0, 0. The E1, E2 here is 0, is 0. E1 is 1, 1, 0. This equation they usually call the saddle points. Saddle points, that means sometimes it's lands on the x-axis or y-axis. And E2 is a constant, is a general form of E1. We can classify and discuss with the saddle point. For the general, for the third choice, yeah, it's consisting the components of x, and we can easily find of y by expressing some this. How to classify this? We can find the delta. The delta is a condition of holding tree, and the condition for the equation existing solution. In this case, they show the condition x in the interval E1 and y is greater than 0. We have two values of x in terms of the solution of quadratic expressed in two points and two values based on the equilibrium points. So now we will discuss the stable of the equilibrium points. Before discuss the stabilities and the bifurcations analysis, we have some mathematical related to this. The first thing is equilibrium points x star is stable if there is the value greater than 0 and the following statement is true. For the value r is smaller than naught, there is existing a value smaller than a big R. To certify this S0 in the bond with S star, and then after that we can find the upper bound existing. So that this value is called the Lobel stable. For detail, an equilibrium points S star is unstable if not stable. And equilibrium point S is asymptotically stable. That's brought to by the line, and it's stable if the conditions following is true. There is 6 R's to certify the value of this, and the limit will apply to the first one. The third chance is equilibrium point X star is marginally stable. If it's stable and not asymptotically stable. This is the definition, and we can use it for the paper. For more detail. For more detail, we can summary the condition for stability, and it's easy to use. It's convenient for investigate the stable of the equilibrium points. For the stable on the real flux, what is the real flux? The real flux up on ancient values of ancient value. That means we need to find the Jacobian matrix, of the model, and let's use the Jacobian matrix. We can choose the agent. We can find the agent values, and we see, and we can find the real flux, because the agent value maybe expressed in the complex number. So if the real flux on the real flux are less than 0, and if the real flux is 0, so if there no TM term, that means some Jacobian term they express in term of exponential term. If not, as usual, we don't need to consider TM. So the solution indicates are bodied in the stable. That means the first case is stable. So the second case is asymptotically stable. If on the real parts of ancient values are less than 0, the solution decays to 0. And the third one is marginally stable. Or if on the real parts and on ancient values are less than or equals to 0, and the real parts, at least one of ancient values is equal to 0. And we also don't need to consider for TM term. For unstable, if on the real parts of the ancient values, at least one of them is greater than 0, if the real part is called 0 also. So the solution is unbounded. Some problems they express the problems in the term of exponential term, and is lambda is an achievement value, and or they can be expressed in this term. So we need to consider for the TM value is m is a positive integer. We usually use in this form. This one. This is not so popular. So apply to the model. The second model. This is the model we have to scale. We can multiply together and express in this sum. So the Jacobian matrix. How to get it? Is there anyone know the Jacobian matrix? How to get the Jacobian matrix? Dr. Trương, do you know?
Yes, I'm still here, and I think it's clear for mathematics. Yeah.
Okay. The Jacobian is we just consider for the linear term. For non-linear, we can ignore linear term here is for x, the constant of x here, minus e, and no y here. The linear term of y is 0. So we got here. And the limit term of phrase is x and no x here. So because it's constant, the coefficient of x is 0. So we write down here. And the minus d. So this Jacobian matrix has eigenvalues. The eigenvalues lambda 1 is minus e, so it's smaller than 0, and lambda 2 is d. Also, E0 is stable because stable based on the condition, the first condition will summarize. And it's also called the asymptotically stable. Okay, we just follow the condition we summarize. So to the same way for at the E1, and we got to Jacobian matrix. The second term here. We also find the negative values of the eigenvalues lambda 3 and lambda 4. And with the condition, no, it's not a condition. We need to find follow the condition, the setting at the beginning, and we can find that lambda 4 is greater than 0 with the condition here. The condition we established at the beginning. Then E1 is a saddle. Yeah. This value is called a saddle. And stable if C smaller than CT. How to find this condition? This condition is based on the definition of stable, of the equilibrium for stable. And this also some words also new to me. And strength reticle, also reticle, we also know reticle is bifurcation. Reticle points, that means it's lie on the body. Strength reticle bifurcation with E3 at the reticle point C. This is the condition we can set up and classify. So the sample at the point E2, and we can we also approach the Jacobian matrix. One of the eigenvalue is positive and E2 is always unstable based on the condition of the model. And we also find the eigenvalues and checking the real parts and the invention, the real parts of the eigenvalues. The main point of this paper is discuss the points E3, and we can see that the E3 is right in terms of the constant of C and D, and in this paper they investigate the changing of the fish point around the fish point, the constant changing around the fish point. So to investigate the constant, we need to use the definition of Hopf bifurcation theory. And in this paper, they also investigate the Buchanov's theorem. But that field is I have not completed, so I just mentioned the Hopf bifurcation. We can investigate one of them. For the definition, we suppose the system in this form as that is not here, and we're not here. So this model is existing the equilibrium points, certify two conditions to confirm for the Hopf bifurcation. The first one is the derivative in terms of fx has symbol pair of uphill imaginary eigenvalues and no other eigenvalue with zero period paths. The second condition for the lambda mean be the eigenvalue dx which are its imaginary at the point set to satisfy the transversality condition. Yeah, transversality condition. We need to find the function of the constant. Actually, we just investigate the Fitzroy, the changing rather of the constant. So this this function is bred in the constant, bred in terms of the constant, and we can use this. Can use the third condition. Use the equation. We can find the function. Find the function. The function by expressed by its constant. In this paper, they express in C or B. The constant of C and B. That means here is the constant, but we consider it look like variable. The constant changing. We change the constant by express. For example, for E is the constant. We can use the transform, the translation by X as not as dash minus E. And after that, we substitute again and substitute X as dash by expressed in terms of the constant of X. To substitute again the model, and we can find the function, the expression of the constant, and we investigate one of the constant. It's based on different model. Different model, we have to investigate the different way. For example, so here, in this paper, they investigate the point S, S3, and Y3. So we got some value, and also mentioned. I think it is similar. So what will we do with the constant like this? I think there are many ways to express the constant here, and I think they use the translation by expressing the term of S3 plus or S3 minus. S3 less or S3 minus is also expressed in the constant, and we can find the S substitute X as that is read by the changing, but that means here the Fitzroy, and we move from the Fitzroy, we can move to another point, and another point also not. Maybe it's not a Fitzroy. Of course, it's not a Fitzroy. So it will run around the Fitzroy. That's the main idea. Mm. 1 minute. My laptop. Okay. I think I missed one place at the last one. Okay. in this paper, I skip the bifurcation because it's so long. We cannot express for all the condition of the terms of the constant term. So now we will move to move to the application, the result of the solution. We use Python, as Python is so convenient in this case. I also prepare this, so we upload the new notebook. No, upload notebook. It's ready. Python. No, here. Where's it? I said it was somewhere. Right. This. No. Model. Okay. Not notebook here. Okay. The models in this paper we will open the paper. You see the paper and the model, and we have the scale. You can separate it. Okay. We can see the model. Yeah. How to perform the solution of the model? There are many ways we can solve by the method. What's it that method? FEM, this method. We can perform the solution of the models by this one, a finite element method or finite difference method, FDM. Finite difference method is most popular for the model, right? For this guy's model. Okay. In this I set up just here some library, or ODE to solve the ODE equation. BLT also, and input the number here, and here's the step for setting the condition of a constant, setting some constant. We put the S value and Y for the empty set. We choose randomly for the constant. And in this in this case, I use the forward LM method. Forward LM method. There are many kinds of type of method we can use. Finite element method, finite difference method, some what method? Let's see. Okay, many I will show you later. So and next here is a setup the loop with the SD. SD is X big X. Yeah. With the index is the values in the difference. And we write this, that means the index is this term they will use the list. The list is the list of the sevens in this term, and setting the next index for the time step. I think it's not very hard, but also we use the stochastics amplifier. We need to define the noise term of better differential equation. And that's after that we set some values which use the function, the library function, to plot it. We need to establish the left like this. And here is the performance of the solution of Predator and Bray. Here is the population size and time. It's also nice. We can choose another color to look like the paper here. Symbol here. It's changing here. It investigates the bifurcation of the constant. It's very nice. And this, the second one is the population. Yeah, the Bray population. We investigate the private population and Predator. And we investigate the perturbation of Bray effect to Bray population. The second method we use is Latka-Bontora. This is also another method to investigate the changing of the solution. We are also established by the same constant and input by the index value, input the model, and set up for the times the time step, and put some plots as label legend, and we can find the deterministic Latka-Bontora. Here is another performance of the model. It's not the same with this, because maybe they use Mathematica, I think. Okay, I think it's on my reset. So is there any question? Are there any questions? We can start step by step. Can you follow? Từ chương. Pass.
Yes, I to follow and can you give us the Python course for this lesson? Yeah.
Okay, we can stop recording.